Okay, so for the last little bit of the year, we're going to talk about redox reactions. And we're going to talk really simply about redox reactions, what they are, how to identify them, and how to tell if a substance is oxidized or reduced. So pretty simple. We're not even really going to get too much into balancing redox reactions. This will be really simple information. Real quick, before we get started, I wanted to remind you that senior finals have been pushed back to Monday, and then junior finals for first period will start on Tuesday, and for third period will start on Wednesday. You can take a look, please take a look at the, hold on, please take a look at the newsletter that I set out on Monday, so that you can get an idea of exactly what is due when. We'll have a lab day for both period on Thursday, and that will be the last lab of the year. And then if you do not have a final, which I'll be sending those emails out to let you know if you do or don't soon, if you don't have a final, the only information that you will be covering on the day of finals is a short quiz for Chapter 19, and that will just include some of the vocabulary, and there is a quizzes in Canvas that you can play to practice the vocabulary, and it will cover some of the stuff that we're going to go over today, like looking at a reaction, what gets reduced, what gets oxidized, what's a reducing agent, what's an oxidizing agent, and that's about it. So let's take a look, okay, at redox reactions. So first things first, what is a redox reaction? Redox stands for oxidation reduction, and it's either called an oxidation reduction reaction or a redox reaction. We're going to call it a redox reaction most of the time, and it is a type of reaction that involves a process called reduction and a process called oxidation. Reduction is what happens when a substance gains electrons and becomes more negative, and oxidation is the opposite. That's what happens when a substance loses electrons and becomes more positive. So one way to remember this is right here. It's called oil rig. It's a mnemonic. Oil stands for oxidation is loss of electrons, and rig stands for reduction is gain of electrons. So if you ever need to remind yourself which is which, you can try oil rig. Oxidation is loss and reduction is gain. Okay. A redox reaction involves a transfer of electrons from one substance to another. So one substance is going to lose electrons. And remember, oxidation is loss, so it's going to get oxidized. And if that substance loses electrons, a different substance in the reaction is going to gain those electrons, to take them. And since reduction is gain, that substance is going to be reduced. The reduction and the oxidation occur simultaneously, which means they happen at the same time. One loses electrons and one takes those electrons. The number of electrons that one substance loses, which is oxidation, will equal the number of electrons that the other substance gains, which is reduction. So you cannot, lose 5 electrons and have the other substance only gain 2. That's not how redox reactions work. If one substance loses 5 electrons, the reduction substance will gain 5 electrons. And how are you going to tell if a reaction is redox? Because some reactions are redox reactions and others aren't. So first we have to take a look at what are called oxidation numbers. You can kind of think of these as the charge. If you remember back in like the first semester, fairly like October, November, fairly early, we were talking about how different groups or columns on the periodic table have different charges. That information is going to come into play here. So we have to talk about oxidation numbers first. So oxidation numbers or oxidation states are the same thing. And basically what that is the charge on an ion or an atom. Okay? Ions, which remember are elements that have a charge, ions in ionic compounds have real charges because electrons have been transferred from one atom to another. So if you remember when we talked about salt, right, we have sodium chloride. Sodium is in group 1 on the periodic table, so it has a +1 charge. And chlorine is in group 17 on the periodic table, so it has a -1 charge. What happens is that the electron gets transferred from sodium to chlorine. And so that is a transfer of electron. That's why it's an ionic compound. So you have a sodium ion, a positive one, and a negative chlorine ion. Okay, so that's a real charge. Atoms in molecular compounds, let's say like water. Okay, water doesn't have ions. Remember we talked about covalent bonds sometimes being like tug of war, and you have some like polar covalent bonds, some of them pull a little harder on the electrons than the others, so they're not transferring electrons. So atoms in molecular compounds like water have what's called apparent charges because there isn't a total transfer of electrons. So that's what I mean by real or apparent. That information isn't going to be on your quiz, but it does help you kind of figure out what's going on when I talk about oxidation numbers. So if I say oxidation number or oxidation state, I mean the charge on an ion or an atom. Okay, they can be positive, they can be negative, or they can be neutral. And when they're neutral, we'll just write a 0. Okay, suggested oxidation states are listed on the periodic table. Remember, if you look on the top of your periodic table, it's kind of, I'm going to do a really bad drawing of the periodic table here. Okay. Okay, on your periodic table, up above the columns, you'll have like a +1, a +2, up above certain columns. Those are suggested oxidation states. So remember, column 1 is +1, column 2 is +2, and then you skip the middle, and then you have +3, +4, -3, -2, -1, and then there's no charge on the noble gases. So you may need your periodic table again for this quiz. Okay, now, for figuring out oxidation numbers, we know what the numbers on, groups 1, 2, and then skip the middle, we know those. But we have some elements that don't follow those rules. So here's the rules for assigning those oxidation numbers, those charges, to different ions. In free elements, each atom has an oxidation number of 0, or neutral. And by free element, I mean any element by itself. So for example, this sodium ion is by itself. Okay, it doesn't say sodium +1, doesn't say sodium 2-, it's just sodium. So it's got a neutral charge. Same with this chlorine gas and this copper. Okay, none of them have a charge listed next to them, and they are by themselves. They're like the chlorine is just bonded to another chlorine. They're not stuck into a compound. They're just by themselves. Okay, so they have a neutral charge, a charge of 0. Then we have rule number 2. Rule number 2 says all metals in group 1, so that's the first column on the left side of the periodic table, have oxidation numbers of +1. And we knew that already. So for example, if you have this compound, KCl, which is potassium chloride, we know because potassium is in that very first group on the periodic table that potassium has a charge of +1. And since we know the compound has to be neutral, then we know that chlorine has a charge of -1. Okay, and then if we look at the sodium oxide on the bottom, we know that sodiums, because they're in the first group, have a charge of +1. And there's 2 of those, so we know that the oxygen in that compound has to have a charge of -2 in order to make the whole compound neutral. Then if we go over one column to the right and we look at group 2, every metal in group 2 has an oxidation number of +2. So here's an example, magnesium bromide. Okay, magnesium is in group number 2, so it has a charge of +2. And then there's 2 bromines, so that means that each bromine has to have a charge of -1 to cancel out the magnesium. This is just like what we were working on back in the first semester. Okay, and then calcium oxide. Calcium is in group number 2, so we know it has a charge of +2. That's the simple rule. If it's in group 1, it has a charge of +1. If it's in group 2, it has a charge or an oxidation number of +2. Group 17, so that's your halogen, so it's all the way over on the right side of the table, but back one. So not the noble gases, but the column next to it. So it's like chlorine, fluorine, iodine, okay? These are usually a charge of -1. So for example, if we look at sodium chloride right here, the salt compound, okay? Sodium we know is in group 1, so it's going to have a charge of +1, and so chlorine is going to have a charge of -1. Okay, chlorine is a halogen. It's in group 17, so it usually does have a -1 charge. Same here. Okay, calcium is in the group 2, so it's going to have a +2 charge. And fluorine, there's 2 of them, and it's in group 17, so it's going to have a -1 charge. Okay? Now, it's important to note that chlorine, bromine, and iodine can have other oxidation numbers, so I would start with anything in group 1 and group 2 first. Use your periodic table. But most of the time, chlorine, fluorine, bromine, iodine, anything in group 17 is going to have a -1 oxidation number. Okay, then rule number 5. In simple ions, so ions that have 1 atom, okay, so like this copper 2+ or this fluorine 1-, these are called simple ions. They're not hooked with anything else, but they're not neutral. They have a charge. Okay, the oxidation number is going to be equal to the charge on the ion. So if it says copper 2+, then the charge on that copper is +2. And if it says fluorine 1-, then the charge on that fluorine is -1. Okay, these ones are really, really simple. If it tells you the charge, that's what the oxidation number is. Okay? Then you have rule number 6. Hydrogen has an oxidation number of +1 in all compounds. Okay, so in water, it's always +1. Okay? Always. In ammonium, hydrogen is +1. So hydrogen is a really good place to start. If you have hydrogen in your compound and you're trying to find oxidation numbers, great place to start because it almost always has a +1 charge. The only exception is if it's in a metal hydride. So that would be, for example, it's paired up with something in group 1 or group 2. So for example, right here, this hydrogen is paired up with potassium, which is in group 1. Well, potassium is also supposed to have a +1 charge. So if potassium has a +1 charge and so if potassium has a +1 charge and hydrogen has a +1 charge, that would have an overall charge of +2, which isn't true. So if it's combined with anything in group 1 or group 2, hydrogen will have a different charge. Okay? So in this case, because potassium has a +1 charge, hydrogen would have a -1 charge. That is the only time that will happen. So you're not going to see that very often because metal hydrides are not very common. So if hydrogen is ever combined with anything from the first or second column on the periodic table, it doesn't have a +1 charge. Start with the metal from group 1 or group 2. But any other time in the entire universe, hydrogen has a +1 charge. Okay, then we have rule number 7. Oxygen has an oxidation number of -2 in every compound. So in water, oxygen has a -2 charge. In ferric oxide, oxygen has a -2 charge. Also a great place to start. The only exception to this rule is when oxygen is in a peroxide. And peroxide just means that there's 2 oxygens and 2 of something else. So hydrogen peroxide is H2O2. There's 2 oxygens and there's 2 hydrogens. That's why it's called a peroxide. That is the only time oxygen doesn't have a -2 charge. In that case, it has a -1 charge. The only other time that happens is if it's combined with fluorine, and then it's actually positive. And the reason that that happens is because the more electronegative an atom is, it influences the oxidation number a little bit more, and fluorine is slightly more electronegative than oxygen. So that's the only time. Oxygen is always -2, unless there's 2 of it and 2 of something else, then it's -1. Or if it's combined with fluorine, then it's +2. But again, these 2 examples are not very common, so you're most likely going to see instances where the oxidation number of oxygen is -2. Then you have rule number 8. Okay, the sum of the oxidation numbers in a polyatomic ion has to equal the charge of the ion. So here's an example of a polyatomic ion, right? You have your phosphate ion. And in your phosphate ion, it tells you right here at the very top what the charge on this ion is. It's -3. And usually when we're figuring out what the numbers of things are, and we practice this in the fall too, but normally we would say, okay, the charge on the phosphorus has to cancel out the charge on the oxygen to make the compound neutral. This charge up here tells us that the compound is not neutral. So whatever the number of phosphorus is and whatever the number of oxygen is has to add up to make -3. So for example, if we start with oxygen, we know that oxygen in this case is going to be -2, but we also know that there's 4 of them, so that's -8. Okay, and then we know that phosphorus is going to have to be +8. Okay, so we know that the charge on oxygen is -2. Okay, And we know that there's 4 of them, so that's -8. And so then we know that phosphorus has to be +5 because we are hitting a -3. So instead of saying, oh, oxygen makes -8, so phosphorus has to be +8, you have to remember that this ion doesn't have a neutral charge, it has a -3 charge. So we have to add the phosphorus charge and the oxygen charge together to make -3. So let's practice again with hydroxide. Okay, hydroxide has a -1 charge. So we know that oxygen always has a -2 charge. Okay, so we're going to start there, and there's only one of them. So we normally would say that hydrogen has a +1 charge, and we can actually still say that because -2 + 1 equals -1, and that's what the charge on hydroxide is. So we didn't have to change anything there. In the last example, we'll look at the sulfate ion. The sulfate ion has a charge of -2. Okay, so we know that whatever we do has to equal -2. Let's start with oxygen because it always has a -2 charge most of the time, and there's 3 of them, so we know that that's -6. Okay, and in order to go from -6 to -2, we have to add +4, so that has to be the charge on sulfate. Okay, and then the very last rule for oxidation numbers is that the sum of all oxidation numbers in a compound has to add up to 0. Now this is a normal compound, so like for example right here in this phosphate ion, right, there's no charge up here on the top right, so it's just a neutral ion. Everything we add together in here, the hydrogen and the phosphorus and the oxygen, have to equal 0. So we're going to start there. We know everything has to equal 0. We know hydrogen, except for in very rare cases, always has a +1 charge, so let's start there. And there's 3 of those, so that's a charge of +3. Then if we scoot over to oxygen, we know oxygen usually has a charge of -2, and there's 4 of them, so that's -8. -8 plus 3 is -5, and we have to get to 0. So that means that phosphorus has to have a charge of +5, otherwise we would never get to 0. Then let's look at manganese nitrate, okay? All right. For manganese nitrate, there's no charge up here, so we know that we have to equal 0. Let's start with the nitrate ion, because the nitrate ion always has a charge of -1, okay? And there's 2 of those, so that equals -2. Manganese then is going to be a +2 because it's in group number 2, okay? And then if we look inside of the nitrate ion, oxygens have a charge of -2, and there's 3 of them, so that makes -6. I'm talking about inside the parentheses now. And then if that's -6 and we have to get to -1, then we know that the nitrogen has to have a charge of +5. So that tells us what the charge on everything in this compound is. Okay, we started knowing that nitrate has a charge of -1, so we looked at what's in this parentheses as a whole. Okay, -1. And there's 2 of those, so that makes -2, which meant that manganese had to have a charge of +2. Then, to get the charge for nitrogen and oxygen separately, instead of hooked together as nitrate, we had to go inside the parentheses. Inside the parentheses, we have an oxygen, and we know that it has a charge of -2. We also know that there's 3 of those, so -2 times 3 means -6. And then, in order to get to -1, which we know is the charge on a nitrate ion, we had to add 5, so we knew that was the charge on nitrogen. Then the last example for finding oxidation numbers we're going to do is sodium sulfate. Okay, so we know that there's no charge up here, so we have to get to 0. Let's start with sodium, because sodium is in the first group, the first column on the periodic table, so it's always going to have a charge of +1. That makes it really easy. And there's 2 of them, so we're up to +2. Then let's swing over to oxygen, because we know that most of the time oxygen has a -2 charge, and there's 4 of them, so that makes -8. So now we're at -8 plus 2, we still have -6, and we have to get to 0. So in order to go from -6 to 0, we have to add 6, and there's only 1 sulfur ion, so that means that the sulfur ion has to have an oxidation charge of 6. All right, so let's recap real fast. What is a redox reaction? Okay, a redox reaction is a chemical reaction where electrons get transferred from one substance to another. One substance is oxidized because it loses electrons and becomes more positive, and the other one is reduced because it gains electrons and becomes more negative. So here's an example, okay? The oxidation numbers for the elements in ferric hydroxide. Okay, we know that hydrogen always has a +1 charge, okay, and there's 3 of those. And then we know that oxygen always has a -2 charge, and there's 3 of those. So that would be +3, -6, so we're still at an overall charge of -3. So that means that the charge on iron has to be +3. Okay. Now, we're going to go into the last part of this, which means if I give you a reaction, how are you going to tell me what gets oxidized and what gets reduced? And what does the oxidizing and what does the reducing? Okay, so let's take an example. Redox reactions are usually synthesis, decomposition, or single replacement reactions. You don't need to know that. I'm just giving you this information so that it's a little bit more compartmentalized. Okay, so let's look at this synthesis reaction, okay? We have copper plus oxygen gas makes copper oxide. If we look right here, okay, that copper is just standing alone by itself, so it doesn't really have a charge. It doesn't have an oxidation number to start with, okay? Same with the oxygen. It's by itself. There's no charge up here, so it's a neutral ion. However, when it makes copper oxide, we know that that's an ionic compound. And oxygen usually has a charge of -2, which means the copper has to be +2. So copper went from neutral to +2. Okay, it got more positive, which means it lost electrons. And if you remember oil rig, right, we have oil, oxidation is loss, rig, reduction is gain. So because copper lost electrons and got more positive, it was oxidized. And since the oxygen got more negative and gained electrons, it got reduced. Okay? And you will see something like this on your quiz, right? Which of these is oxidized and which is reduced? And you have to take a look and say, okay, which one got more positive? That one was oxidized. And which one got more negative? That one was reduced. And we will, on Monday, and on Friday, I'll give you kind of some practice sheets to kind of go through and practice stuff, and you are welcome to shoot me emails and stuff while I'm gone on Friday and Monday, and we will get everything figured out. Okay, let's take a look at this example down here, okay? You have potassium chlorate turns into potassium chloride and oxygen, okay? So if we look here, okay, we know that potassium is in group number 1, so it has a +1 charge. Okay, I'll get rid of that so you can see that. It has a +1 charge. Then you have chlorine and you have oxygen. Oxygen always has a -2 charge, and there's 3 of them. Okay, so that means that the overall charge on chlorine has to be 5 because +1 + 5 minus 2 times 3. And that's an overall neutral compound. Okay, so now we know the oxidation numbers that we started with. After the reaction happens, potassium still has a charge of +1. Chlorine now has a charge of -1 though, so that it can balance out the potassium. And oxygen is chilling over by itself, so it has a neutral charge. Okay, so now we have to say, okay, what got oxidized? What became more positive by losing electrons? Okay, so we had potassium went from +1 to +1, so it didn't change. Chlorine went from +5 to -1. So it got more negative, it didn't get more positive. Oxygen went from -2 to 0. Oh, that one got more positive because it lost electrons, which means it was oxidized. Okay, and then if we look at what gets reduced, we're looking for what got more negative because it gained electrons. Potassium stayed the same. We know oxygen was reduced or was oxidized, so chlorine went from +5 to -1. Got more negative because it gained electrons, so that was reduced. Okay, let's look again. Number 3. Okay, we have magnesium by itself plus copper oxide makes copper plus magnesium oxide. Okay, so let's go ahead and start assigning numbers. Let's start with magnesium. Magnesium is by itself. It doesn't have a charge listed next to it. Easy peasy, that's a 0. It's neutral. Okay, now let's take a look at copper oxide. Okay, it's in a compound, so let's break it down. Let's start with oxygen first, because that's easy. It usually has a charge of -2. And in order for this whole compound to be neutral, we have to cancel out the -2. So that means copper has to have a +2. Then we go to the right side of the arrow. Copper's chilling all by itself, so that means it's neutral, has a charge of 0. And then we do the same thing that we did on the other side. Let's start with oxygen. Actually, let's start with magnesium because it is in group 2. So it always, no exception, has a charge of +2. Okay, when it's in a compound. And then that means oxygen has to have a -2 charge. So now we have to see which ones get oxidized and which ones get reduced. Okay, so let's start with oxidation. We know that if it gets oxidized, it is losing electrons and getting more positive. So magnesium went from 0 to +2. It got more positive, so that means it was oxidized. Okay, now which one got reduced, copper or oxygen? So copper went from +2 to 0, so it got more negative, and oxygen went from -2 to -2. It stayed the same. So since copper went from +2 to 0 and it got more negative, that's what got reduced. Okay? Okay. So in all of these types of reactions, didn't matter if it was synthesis, single replacement, whatever, something got oxidized and a different substance got reduced. Okay? In a redox reaction, we can identify what's called an oxidizing agent and a reducing agent. Okay, this part can confuse some kids because the oxidizing agent is the thing that causes something to be reduced, and that causes something to be oxidized, and the reducing agent causes something to be reduced. Okay? So an oxidizing agent causes the oxidation of another substance. It's the thing that gets reduced. So whatever gets reduced is the oxidizing agent, and whatever gets oxidized is the reducing agent. They're opposite. The agent is opposite of what happens to it. Okay, and that's because the oxidizing agent helps oxidize the other thing, so it has to be reduced because it's taking the electrons. And the reducing agent is the opposite. The reducing agent causes the reduction of another substance because it's the thing that is oxidized. It helps reduce the other substance by giving up some of its electrons. Okay, so the oxidizing agent and the reducing agent are always reactants. It's never, ever, ever going to be a product. Okay, the agents have to be reactants. So let's look at examples. Okay, the examples say assign the numbers like we've been doing, and then identify the oxidizing and reducing agents. So let's start here. Okay, copper oxide. Oxygen is pretty easy to identify. It's usually -2. And there's no charge on that compound, so to cancel it out, copper has to be +2. Hydrogen is hanging out by itself, so it has no charge. And then on the other side of the arrow, copper's hanging out by itself, so it has no charge. And then if we start with hydrogen, it's always +1 for the most part. And then that means that because there's 2 hydrogens, oxygen has to be -2. So which one is the oxidizing agent and which one is the reducing agent? First, let's figure out which one is oxidized and which one is reduced. Okay, remember, oil rig, oxidation is loss, so it gets more positive, and reduction is gain, it gets more negative. So copper goes from +2 to 0. Okay, it got more negative. So that means that copper was reduced. Okay, and then oxygen went from -2 to -2, so it didn't change, so we can leave it alone. Hydrogen went from 0 to +1. It got more positive, so that means that it was oxidized. Okay, so now that we know what got reduced and what got oxidized, we can figure out what was the agent. Okay, the oxidizing agent is whatever got reduced, so that's copper. And the reducing agent is whatever got oxidized, so that's hydrogen. Just remember that the agents are opposite of what happened to it. So because copper got reduced, it's the oxidizing agent. And because hydrogen got oxidized, it's the reducing agent. Okay? All right, let's do another example. So we have zinc. It's hanging out by itself, so it has a 0 charge. Okay? Then we have copper chloride. Chlorine usually has a charge of -1, and there's 2 of them, so that means copper, in order to cancel that out, has to have a +2 charge. Then let's go to the right side of the arrow. Start with chlorine again. It's usually -1. There's 2 of them, so that means that zinc has to have a +2 charge. Copper's hanging out by itself, so it's got a 0. Okay, so let's take a look at what was reduced. I'll put a circle around what gets reduced, and I'll put a square around what gets oxidized. Okay, so let's take a look at what gets oxidized. So that means that it lost electrons and got more positive. Zinc went from 0 to +2. It got more positive, so that guy was oxidized. Okay, then we have chlorine went from -1 to -1. It didn't change, we can ignore it. Copper went from +2 to 0. It got more negative, which means it was reduced. Okay, the oxidizing agent is whatever got reduced, so that's copper, and the reducing agent is whatever got oxidized, so that's zinc. We'll do one more example for this. Okay, so we have methane and oxygen. Let's start with the hydrogen and methane. There's 4 of them, and they each have a +1 charge. So that means that the carbon has to have a -4 charge. Oxygen is hanging out by itself, so it's got a 0 charge. And then in carbon dioxide, oxygen has a -2 charge usually, which means since there's 2 of them, carbon has to have a +4 charge. And then if we look at water, start with hydrogen, +1, and there's 2 of them, and so that means that oxygen has to be -2. First, what gets oxidized? Okay, oxidized is a loss of electrons, so it gets more positive. So carbon went -4 to +4. Okay, hydrogen went +1 to +1, didn't really change. Oxygen went 0 to -2. Okay, so which one got reduced? Or sorry, which one got oxidized? Oxidation is loss, so it got more positive. Okay, so that's going to be our carbon. Oops, sorry, that should be a square. Get rid of that. Okay, so since carbon went from -4 to +4, it got oxidized. Hydrogen didn't change, but oxygen went from 0 to -2, so it gained electrons, which means that it got reduced. Okay, the oxidizing agent, opposite, is whatever got reduced. So that's your oxygen. And the reducing agent is the opposite, which is whatever got oxidized. So that's your carbon. Okay, as a quick review, your oxidizing and reducing agent definitions. Okay, oxidizing agent causes oxidation. It's whatever got reduced. The reducing agent causes reduction, so it's whatever got oxidized. Okay? And that is it. Okay, there will be a little packet. I can hand that out. I can leave that with the sub-plans today. That way you can start taking a look at that and getting that practice in well before seniors take the Chapter 19 quiz on Monday for 3rd period and 1st period. And then you underclassmen can finish this packet on Monday as well to get practice in before their final begins. Remember, no matter if you have a final or not, you're going to have this short little quiz on this information that I just gave you. It's not going to be super hard. It's going to be mostly vocab and just what we did. What's the oxidation number? What gets reduced? What gets oxidized? What's the oxidizing agent? What's the reducing agent? It's not going to be hard. It's not going to be more than a page long. So whether you have a final or not, you will have that. And then if you do have a final, you'll also start your final on that day. Keep an eye on your emails. I'm going to be sending you all of your stuff to let you know if you have a final or not, and if you do, what's going to be on it. If you have questions, catch me in the hallway. I'll be around town. I guess that would be today for you, Wednesday the 11th for town cleanup day. I'll be in school all day Thursday, and then I will be gone Friday and Monday, but I will try to answer my email. So if you have questions, please shoot me that email, and we will try to get everything figured out. Thanks.